Hi, chemistry. I want to talk to you today about a concept that we are going to start talking about more and more as we talk more about reactions. As we start looking more about reactions, we're going to have to talk about reactions and quantify reactions, or talk about reactions in terms of the numbers that occur as reactions proceed, right? Like, how many grams of reactant do we use or do we produce? Or how many liters do we need or do we make? Or what about an amount? Can we talk about a counted amount? So, as we start to look at these numbers inside of reactions and start to quantify reactions, we're going to use a skill called dimensional analysis in order to deal with these numbers. So I want to introduce you to this skill of dimensional analysis today. And so we can start looking at this within our reactions. So dimensional analysis is a skill of analyzing a question in terms of the dimensions that are given to you. Now, dimensions might be kind of a strange term for us. In science, for ages, you have talked about dimensions, but you probably haven't called them dimensions. What you've called them are units. And so dimensional analysis is analyzing a situation based on the units that are present, or letting the units lead us through our question or to our answer. So let me show you what I mean in terms of something very simple, like a conversion between meters and kilometers. Now, I know you've done this before. You may have actually already used dimensional analysis as you try to work through things in meters or kilometers. So what we're looking at really when we talk about meters and kilometers is usually a conversion. We're going to have some distance. Let's say we're looking at a track, a high school track, which is 400 meters all the way around. But we don't want to talk about the track in terms of meters. We want to talk about the track in terms of kilometers. So what is this amount in kilometers? That would be our question. Like I said, it's a really simple question, and you probably can come up with a couple different ways to deal with this question. But I want to take this simple question that you already know how to deal with, and I want to show you how we would solve it using dimensional analysis. Now, you may try to solve this using something like proportions, or just by thinking about the conversion inside your head. But when we use dimensional analysis, we're going to look at the dimensions. We're actually going to set up this whole problem in terms of the dimensions and allow those dimensions or those units to lead us through the problem. Okay, so it would look something like this. We would start with what we're given, which is 400 meters, right? And then we would try to find what we want in the end. In this problem, we want those meters to be changed into kilometers. Now, in the middle here, I'm going to put an equal sign there. In the middle here, what we do is we set up a conversion factor. Now, we're not actually changing the amount that we're given, right? We start with one high school track. We end with one high school track. All we're doing is we're talking about the units differently, right? First, we're talking about it in terms of meters. Next, we're talking about the exact same difference in terms of kilometers. So in the middle here, we're going to set up a conversion factor. And this conversion factor is going to convert us out of meters and into kilometers without actually changing the distance that we're talking about, right? We still want to end in a track. So I'm going to multiply by a conversion factor. And here's where dimensional analysis happens. I want my meters to go on the bottom, the thing that I'm given that's currently on the top, I want it to be on the bottom. And the thing that I want to end in, kilometers, needs to go on the top. Now, here is their relationship to one another. So I'm going to put that relationship or that ratio that is constant. I'm going to put that in the middle. And so now you see I have meters on top, meters on bottom. Those are going to reduce out. I have kilometers left. That's what I want in the end. And then I can do the math. I can deal with the numbers on the calculator. So 400 times 1 divided by 1,000 is going to give us, let me erase that question mark, 0.4 kilometers. Okay, so I want to pause here and say, I know you know how to do this another way. So the reason we're going through this is because I want you to learn the skill of dimensional analysis. I don't really care if you can convert between meters and kilometers. I mean, it's useful, right? It's something we want to be able to do. But there's a bunch of different ways that we can get to this answer. So the answer is not really what I care about. It's the skill of dimensional analysis that I want us to start seeing and wrapping our brain around. Now, we're going to break dimensional analysis down a little bit in this video. And we're going to talk about what just happened inside this problem a little bit more. But let me show you a couple other things to try to pitch this idea of why dimensional analysis is so very useful to us. Okay, first of all, if I know how to use dimensional analysis, I can use this idea right here of the relationship between meters and kilometers to get out of meters into kilometers. I can also use it to do the opposite, to get out of kilometers into meters. Let's say you know the distance between your house and a store is 1.2 kilometers, right? We can use this same idea. We want to get out of kilometers into meters. I use that relationship between them to get into meters, right? I can go both directions. I can get out of meters or I can get out of kilometers. It's also, dimensional analysis is also particularly useful when you have a bunch of different units that you have to bounce between. Let's say they start us in feet, for example. Let's say they start us in, 5.9 feet, and we want to get into kilometers, right? Well, we can use dimensional analysis to get out of feet into inches, out of inches into centimeters, out of centimeters into meters, out of meters into kilometers. So I've just set up this enormous problem bouncing between a bunch of different units, and all I have to look for is these ratios. Well, what is the relationship between inches to feet? What is the relationship between centimeters and inches? How about centimeters to meters? How about meters to kilometers? If I know all of these ratios and I know the skill of dimensional analysis, this really complicated problem all of a sudden becomes fairly simple. Additionally, as you keep going in chemistry, using the units to solve for something that you want becomes extremely useful. And we see this in this example with specific heat here. This is the specific heat of water. And if I just know this one specific heat of water with all of the different units, I can find a ton of different stuff, right? If I have, let's say I have a bucket of water, and that bucket of water weighs 150 grams, and I want to raise the temperature of that bucket of water by 2 degrees Celsius. Well, I can use dimensional analysis to figure out how much energy to put in. All I have to do is arrange the units that I'm given to reduce out to the one unit I want to be left in, right? I have grams. I can multiply by grams and reduce out grams. I have Celsius. I can multiply by degrees Celsius. And the one unit I'm left with is joules, right? I just set up my problem by only looking at my units. And now that I've set up my problem by only looking at my units, I can go back and deal with the numbers and find whatever my answer is going to be in joules. So if you know how to look at the units and set up your problem with the units, you can solve these incredibly complicated scenarios, or you can deal with this context that is very tricky conceptually to deal with. You can deal with the math, and the math almost helps you understand the concept. But you must know the skill of dimensional analysis. Being able to deal with it in proportions is not enough. Being able to understand it conceptually is just not going to happen. A lot of times you have to set up the math and then the concept falls into place. It's a support, it's a strength, right? So that's why we're talking about this idea of dimensional analysis. So let's break it down just a little bit more. And then we'll go back and try some practice. Okay, so the premise of dimensional analysis, really the catch on dimensional analysis, comes down to this concept. What is x over x? And you may be able to tell me already, what is x over x? And if you can't tell me, let me kind of lead you there. What is 4 over 4 equal to? That's equal to 1, right? If we have our total thing has 4 pieces, and we have all 4 pieces of that thing, we have one whole thing, right? 4 over 4 is equal to 1. What's 400 over 400? Same idea, it's equal to 1. Well, what if you have something that has X amount of pieces and you have X amount of pieces? It's equal to 1, right? So this is the concept that dimensional analysis is built upon. Because in that example we just saw, if we have 1,000 meters equal to 1 kilometer, look at what I have. I have meters over meters. If 4 over 4 is equal to 1 and x over x is equal to 1, well, meters over meters is also equal to 1. So that's why if you have a unit on the top of your fraction and you have that same unit in the denominator of your fraction, those are going to be equal to 1. So they reduce out of your equation, right? So this is kind of the premise that dimensional analysis is built off of. You have to understand that. Another thing that you really have to understand when you're walking in a dimensional analysis is that if you have a number, like let's say we have 400 meters, right? That 400 meters is actually a fraction. It's 400 over 1, right? The 400 is actually in your numerator. You have a 1 in your denominator. We just don't typically write the 1. If I am 65 years old, when I'm actually 65 years old, this recording will be very funny to me. If I am 65 years old, that's actually a fraction that we're talking about. It's 65 over 1. So you have to remember this when you're doing dimensional analysis, because if you have 400 meters and you multiply it by 1 kilometer over 1,000 meters, right? You have to know how to multiply these numbers, 401 and 1,000. And in order to multiply them correctly, you have to remember that the 400 is actually in the numerator. You have a 1 in the denominator. And this leads us to the third math skill that you really need to know in order to deal with dimensional analysis. When you multiply fractions, you have to multiply across the top and the bottom. So this would actually turn into 400 times 1 over 1 times 1,000. When you multiply by fractions, multiplying fractions, you're going to multiply the numerator. You're going to multiply the denominators. And then what you do is you take those products. 400 times 1 is 400. 1,000 times 1 is 1,000. And then you divide. Okay, so you have to know how to multiply fractions. The skill that gets confused with multiplying fractions is setting up proportions. So if we were dealing with proportions where you cross multiply, it would look like this. You would have an equal sign in between your two fractions. And instead of putting meters on the top and meters on the bottom, like we do in dimensional analysis, in this other skill of dealing with proportions, you would match the meters. And you would have a variable in there, okay? And that's when you would cross multiply. So we're not dealing with proportions. In fact, we're trying to get away from proportions. Proportions is another way to deal with conversions, but proportions gets really difficult to deal with when you have 4 or 5 or 6 or 7 different conversions that you have to set up. Which is why we're not dealing with proportions. I'm trying to teach you a new skill of dimensional analysis. So remember that when you multiply fractions, you multiply the numerators, you multiply the denominators, and then you divide numerator by denominator to get your answer. Okay, so those are the 3 math skills that dimensional analysis is built upon. I know I went super fast through those, but it's because I'm pretty confident that you guys are proficient in those math skills. But if you want to talk through those slowly or go through a couple more examples of using those math skills, I am more than happy to do that with you. All right, so in order to work with dimensional analysis, you must deal with conversion factors. Like I said, if we're setting up a very simple problem, what we would do is take the thing we're given, and we would have that given unit, and we're going to multiply that by a conversion factor. Now, the conversion factor must have 2 units. If the thing you're looking at does not have 2 units, it can't be a conversion factor. Another thing the conversion factor has to have is that the top is going to be equal or equivalent to the bottom of the fraction. And we saw this in the last example. 1,000 meters is equal to 1 kilometer. Those are the same distance. If you walk 1,000 meters, you have walked 1 kilometer. Those 2 distances are equal. And so a conversion factor is going to have these 2 equal or equivalent quantities in 2 different units on the top and the bottom. And what you do by multiplying the thing that you're given by a conversion factor, you are essentially multiplying by 1, right? If you have the same thing on the top and the bottom, that fraction's equal to 1. And that's why we can just change the units without changing our distance, right? If we take a high school track of 400 meters and we multiply it by a conversion factor, 1 kilometer over 1,000 meters, what we get is that same distance, the same high school track in kilometers. We've taken our high school track, we've multiplied it by 1, right? Just 1 in 2 different units, and we end up with the same distance in a different unit. That's what a conversion is, and that's why dimensional analysis works. You must, whatever your given unit is, must be on the bottom so that they reduce out. You have your new unit on the top, and that's the unit that your answer is going to be in. Okay, so we have to be able to recognize conversion factors. Sometimes these look like things that are equal. For example, 2.54 centimeters is equal to 1 inch. That could be written as a conversion factor. 2.54 centimeters and 1 inch are the same. Now, because they're both equal, it doesn't matter if you write it with centimeters on the top or you write it with inches on the top. It can be written either way you need it because the two things are equal. Similarly, 7 days to 1 week. That could be used as a conversion factor because 7 days is equal to 1 week. 12 donuts is equal to 1 dozen donuts. Those two things are equal quantities communicated in different units. So you can put those together to make a conversion factor. 12 grams of carbon is equal to 6.02 times 10 to the 23rd atoms of carbon. Those two things are equal quantities, and so they can be put into a conversion factor. And here we see another thing. Sometimes conversion factors are written as equivalent statements. Sometimes conversion factors are written as fractions. When we use them in dimensional analysis, we're going to use conversion factors as fractions. They can also be written out in a sentence like 1 inch is equal to 2.54 centimeters. Okay, we have a conversion factor there that's written as a sentence. In order to use it in dimensional analysis, we're going to have to put it into a fraction. Okay, so some of our conversion factors can be things that are equal. Some of our conversion factors can be things that are equivalent. Now, this is usually talking about a very specific scenario. So, for example, at birth, there are 1.03 males to every 1 female. That can be a conversion factor if you're dealing with birth rates. So, in a similar context, you can use that as a conversion factor. At birth, 1.03 males equals 1 female, or 1 female over 1.03 males, or 1.03 males over 1 female, right? So in that specific context, we can use that equivalence statement as a conversion factor. Now, in a different context, it's not true. If we look at humans at age 50, this ratio is no longer a true statement and we can't use it for humans at age 50, but we can use it within this context at birth. Same thing in my dresser, one pair of pants. I have one pair of pants for every 3 shirts. That's a ratio that's true for my dresser. So if you're dealing with conversion problems specific to my dresser, you could use that as a conversion factor. But that ratio might not be true for your dresser, right? So that ratio is equivalent as long as you're talking about the same context, my dresser. Once you switch context and talk about someone else's dresser, the equivalent statement might not be true anymore. In banana cake, you use 2 eggs for every 1 cup of flour. That is a true conversion factor for banana cake. But once you make muffins, that might not be true anymore, and you can't use that ratio. In the combustion of hydrogen, you use 2 hydrogen molecules for every 1 oxygen molecule. So 2 hydrogen molecules for every 1 oxygen molecule can be used as a conversion factor as long as you're dealing with the combustion of hydrogen. Once you're dealing with a different reaction, let's say the decomposition of baking soda, this ratio is not true for the decomposition of baking soda, and you can't use it anymore. So equivalent statements can be used as conversion factors as long as you match the context. Okay, lastly, you might have to write your own conversion factor based on the context that is given to you. Let me give you an example. All right. Each milliliter of silver weighs 105 grams. And then they go on to talk about a silver statue, right? So here, this sentence gives me an equivalence statement. Each milliliter of silver weighs 105 grams. So it's in a sentence, but they're telling me 2 things that are equal. So I could write 1 milliliter of silver equals 10.5 grams of silver. I could write 1 milliliter of silver over 10.5 grams of silver. I could write 10.5 grams of silver over 1 milliliter of silver. And I can use these as a conversion factor because the top is equal to the bottom, or the top is equivalent to the bottom in a specific scenario. And therefore, I can use it to convert units, milliliters, and grams of silver in dimensional analysis. Okay, so we're understanding what dimensional analysis is and why we're learning it as a skill. We're understanding a couple different math skills that we need to be functional in order to use them in dimensional analysis. And we're understanding a little bit more about what a conversion factor is that we can use in dimensional analysis. Okay, so these are very basic things. If we continue on, I have a couple examples for you, and these examples are specific to our favorite neighbor, Mr. Mig. Not that our other neighbors are not favorite, but Mr. Mig just happens to love Mountain Dew. I don't know if you knew this about him. So I have a picture of Mountain Dew here, and we have a bunch of different examples of things we can deal with the Mountain Dew. We're going to deal with the numbers of Mountain Dew, the quantitative analysis of Mountain Dew, and we're going to try to use dimensional analysis to figure this stuff out. So our new favorite skill, dimensional analysis. I would love if you paused the video here and you tried these together. I'm going to post a different video where I show you these solutions, but let's see what of these skills that we talked about today can you put into practice? So number 1, can you pull conversion factors out of these 4 different questions? Can you figure out what you're given? Can you figure out what you're trying to find? So if you can figure out those three pieces, what are you given? What's your conversion factor? What are you trying to find? Now, can you put them all together into a dimensional analysis problem? Okay, so try this. Let me know what questions you have, and then we'll go through this together.